Okay, picture this. You're sitting in a packed coffee shop. You've got the clinking of espresso cups, people laughing at the next table, traffic outside, the whole shebang. Yet somehow, you can completely focus on the person sitting right across from you. Your brain just tunes out the noise. It's basically a superpower we use every single day without even thinking about it. But how do you teach a machine to do that? Well, that right there is the absolute core challenge of teaching AI to isolate a single voice in a totally chaotic room.
So let's get into this explainer. Today, we're unpacking a really wild paper. It's called Flexible Multi-Channel Target Speaker Extraction Using Geometry Conditions Spatially Selective Nonlinear Filters. I know, that title is a total mouthful, but the actual goal here is incredibly cool. It's all about making AI audio filters super flexible. See, right now, our devices are kind of rigid. They need the world to cater to their specific hardware design. This research, it completely flips the script. It's about building AI that actually adapts to the chaotic world around it, rather than forcing the world to adapt to the AI.
Here's our quick roadmap for today. We're going to cover 1. The target speaker problem. 2. Meet the research team. 3. The geometry condition solution. 4. Testing the new filter. And finally, 5. Real-world audio applications.
All right, Section 1, the target speaker problem. So, to really appreciate the fix, we kind of need to understand the baseline problem first. In the acoustics world, they call this the cocktail party problem. Imagine, you want to isolate a target speaker coming from a very specific angle. Researchers call this angle the direction of arrival, or DOA. Now, smack in the middle of this room, you have a microphone array, just a bunch of mics picking up sound. Traditionally, we use algorithms called spatially selective nonlinear filters, or SSFs, and they do a decent job, but they completely rely on knowing the exact precise distances between those fixed microphones to create an audio mask. That mask acts like a sieve, filtering out the background junk so you only hear the person you actually want to hear.
But here's the massive flaw where this old system just totally falls apart. Traditional AI models are basically like prescription glasses permanently glued to your face. They work perfectly if you have the exact, specific circular microphone array they were trained on. But if you take those exact same mics and scramble them into some random geometry, the AI literally goes deaf. It completely loses its ability to map the audio because the physical layout of its ears just changed. It's expecting mics to be exactly 2 inches apart, but now they're scattered all over the place, and the algorithm just breaks.
Moving on to Section 2, meet the research team.
This absolutely brilliant fix comes to us from Jiatong Li, Wiebke Mittelberg, and Simon Docklow over at the University of Oldenburg in Germany. And honestly, what they set out to do was super ambitious. For literally decades, being stuck with fixed hardware geometry has been this stubborn roadblock in audio engineering. They wanted to build a system that wasn't stubbornly tied to one specific layout, but could dynamically adapt its hearing to, well, literally any layout you throw at it, as long as the total number of microphones stays the same.
Let's dive into Section 3, the geometry condition solution.
Okay, the real magic behind this newfound flexibility is something called the film layer. That stands for feature-wise linear modulation. Think of film like a universal adapter for the AI's brain. It lets the AI swap out its custom prescription glasses on the fly, based purely on new geometry data. Instead of hardwiring the exact mic positions deep into the neural network, the film layer takes an external input that says, hey, here's exactly where the microphones are right now. Then, it uses that spatial data to actually tweak or modulate the AI's internal processing in real time. It's such a clever way to detach the software's listening ability from the physical hardware.
So conceptually, the whole architecture is called the Geometry Conditioned SSF, or GC-SSF, and the design is just elegant. The standard audio processing blocks operate normally, but now they run alongside this totally new conditioning branch. This branch takes the exact mic coordinates and the target speaker's direction and encodes them into a feature they call DOA-MPE, which stands for Direction of Arrival combined with Microphone Positional Encoding. Basically, it mathematically mashes up where the sound is coming from with where the mics actually are. Then, this branch acts like an orchestra conductor, actively telling the main network how to listen based on that exact physical setup.
It all boils down to 3 really logical steps. Step 1. Generate that spatial encoding, the DOA-MPE, which captures all the essential timing delays between the scattered mics. Step 2. Process that encoded data through a 1D convolutional encoder so the system truly understands the spatial layout. And Step 3. The absolute magic moment. Inject that spatial data directly into the main filter's workflow through those film layers at specific injection points. By doing this, the AI isn't just mindlessly processing sound anymore. It suddenly gains real-time awareness of its own physical layout. It finally knows the shape of its own ears.
Now for Section 4, testing the new filter.
The theory sounds great, right? But what happens when we actually scramble the microphones in a lab and test it? Well, the PESCA scores, which is basically a standard metric where higher means clearer speech, tell a wild story. Check out the baseline model. When it's trained and tested on the exact same circular array, it gets a really solid 2.95. But test that same model on a random scattering of mics, and it plummets to 1.16. To put that into perspective, a 1.16 is just garbled nonsense. It's actually worse than listening to the completely unprocessed raw audio. But then, look at the new GC-SSF model. It stays incredibly robust, sitting right around 2.4 to 2.5 across all shapes. It literally makes the physical layout irrelevant to the audio quality.
That right there represents up to a massive 1.25 jump in the PESC speech quality score compared to the old fragile baseline. Let that sink in for a second. In audio processing, a jump of 1.25 is absolutely night and day. We're talking about the difference between indistinguishable robotic static and crystal clear human speech. It is just a huge, monumental win for adaptability.
But wait, we have to ask, is this system just doing some generic blanket noise reduction, or is it actually listening directionally? So the researchers set up a stress test. They essentially lied to the AI. They'd tell it the speaker's at 90 degrees when they're actually at 45. And as you can see, as that error increases, the GC-SSF's performance drops sharply. Now, counterintuitively, we actually want to see that steep drop. It proves the system is highly spatially selective. It's acting like a highly trained sniper, not a scattergun. It aggressively filters out absolutely everything except the specific coordinate it was told to focus on.
So, comparing them directly, it's a total game changer. The GC-SSF takes a fragile system that completely breaks under real-world variation and turns it into a robust, highly adaptable machine. By explicitly feeding the geometry to the AI instead of hiding it in the training data, this totally bridges the performance gap. We are fundamentally shifting from relying on rigid hardware to leaning on flexible, intelligent software.
Finally, Section 5, Real-World Audio Applications.
So, why does all this complex math actually matter to us in our everyday lives? Well, for starters, hardware companies won't have to spend a fortune retraining AI models every single time they move a microphone hole slightly to the left on a new laptop or smartphone. But the really exciting part, this paves the way for what they call ad hoc acoustic sensor networks. Imagine you're back in that noisy coffee shop trying to take a Zoom call. You've got your phone on the table, a smartwatch on your wrist, your laptop open. Right now, those are three totally isolated devices. But with this breakthrough, those devices could seamlessly network their scattered mics together in real time. The AI maps out the random geometric layout on the fly, and boom, it creates a virtual super microphone that isolates your voice perfectly and totally mutes the cafe around you.
By finally severing that hardwired restrictive link between the AI's processing brain and its physical hardware ears, these researchers have unlocked a massive new frontier. And it leaves us with such a fun question to ponder. What incredible things are we going to build? And how will our devices evolve now that the hardwired limitations of robotic hearing are finally broken? Thanks so much for joining me for this explainer, and I'll catch you on the next one.